All right, there we go. So, as you saw in our introduction there, the syllabus, some of the topics in this course go back to some of the very basics. There's two reasons for that. One is I found that students who struggle with algebra and some of the more difficult topics, the reason is they may have been able to do some of the easier topics, but they didn't really understand why they were doing it. So we go back to the basics, and I'm going to try to give you a little bit of a deeper perspective as not only how you do the things, but why it is that things work the way they do. So to give you an example of that today, not to get too deep into it on the first day, but let's look at probably the most basic concept in math, but also one of the most misunderstood. And that is the concept of a number. If I put a 4 up here, show of hands, how many of you would tell me that that's a number? Most people would, right? Well, technically, that is just a numeral. It's an amount telling us how many. To be a number, it has to have two pieces. It has to tell us how many, but it also has to tell us of what. So it might be 4 cows. Now that's a complete number. It has this amount, the 4, which tells us how many. I'm going to call that the name. And it has a label. In this case, the cows. Oops, name, what do I mean? That's what I get for coming to work totally sober for once. The 4 is the amount, which tells us how many. I'm going to call that the count. The cows is the label here, which tells us of what. What is it we have 4 of? I'm going to call that the name. Makes more sense that way, right? Okay. I'm not doing that because I'm not one of those instructors that if you don't label your answers is going to mark it wrong. That's not my purpose for going over this. The purpose is those two parts of the numbers, if you understand how they work, it explains how all of our basic operations work. So let's take a look at those two parts of a number within our most basic math operations. So our two most basic math operations are addition and multiplication. Now at this point you might be wondering, wait a second, where's subtraction? I thought addition and subtraction were our basic operations. Well, addition and subtraction, if you really get deep into number theory, they're the same operation. In fact, there is no subtraction. Subtraction is just addition done in reverse. We're not going to get quite that technical. There is subtraction, but addition and subtraction are really the same operation. So any rules that we talk about for addition also apply to subtraction. And then, of course, the same thing for multiplication and division. They're the same operation, just one is going forward and the other is reverse. So let's take a peek at, let's do like 4 inches plus 7 inches. What do we get? 11 inches. Good. So if we look at our counts, we have the 4 and the 7. What did we do with those? Well, became 11. We added them. We combined them with addition. So when we add numbers, we combine the counts. But what happened to our names? We had inches, and it became still inches. It stayed inches. When we add or subtract, we just keep the same name. Now you might be looking at that thinking, yeah, okay, that's not terribly interesting. Probably not quite worth your $450 for the course yet. But let's take a look at the difference between that and then what happens in multiplication. Let's take 4 inches times 7 inches. You guys all familiar with the dot for multiplication instead of the x? It means the same thing. So 4 inches times 7 inches gives us 28 what? Not inches, but inches squared. If you think about it, if you're multiplying two lengths, chances are you're looking at two sides of a rectangle, you're looking at an area. So if we look at what happened there with our counts, we have the 4 and 7. They became 28. So we still combined them. This time we're multiplying, so we combined them with multiplication. So we still combine the counts. But the difference came here with the names. We had inches and inches, and it became inches squared. When we multiply, we also combine the names. Now you might be looking at that and say, well, that's kind of a subtle difference. What does it matter? Well, when we look at our other forms of numbers, it explains all those things that we thought were special rules for that form of numbers. It all comes down to those two little things right there. When we add numbers, we combine the counts and keep the same name. When we multiply numbers, we combine the counts, and then we also combine the names. In fact, it even tells us what numbers we can even use in each operation. For example, let's say we have 3 cows plus 5 boys. Does that give us 8 cowboys? No, it doesn't work that way, does it? How about if we go the other way? 5 boys plus 3 cows. Does that give us 8 boy cows? Anybody have a farm background in here? Nobody? No. If you know anything about farming, you can tell me that's a whole bunch of bull, right? Okay, a long way to go for a joke. I'm a math teacher, which means I'm required to have a really stupid sense of humor to get used to. It's a long way to go for a joke, but there's a point behind it. The point being, when we add numbers, we're going to keep the same name, which implies we had to start with the same name. Inches and inches, we kept it as inches. Down here, we didn't have the same name, so we don't know which one to keep. So we can't combine them if they don't have the same name when we add. So to get a little bit less of a nonsense example here, if I had 5 feet plus 2 pounds, what do I get? I get 5 feet and 2 pounds. They have different names. I cannot combine with addition and subtraction, feet and pounds, because they have different names. However, with multiplication, if I had 5 feet times 2 pounds, when I multiply, I'm going to combine the counts. 5 times 2 is 10. But I also combine the names. Feet times pounds is just foot-pounds, which is a unit of torque. Or if you're in construction, that's a unit of bending moment in a beam. When I multiply, because I'm going to combine the names, I don't have to start out with the same name. That has a huge consequence now, like I said, when we look at our rules for our other forms of numbers. So let's look at one of our other forms of numbers. In fact, let's look at everybody's favorite form of number, fractions. Now, I saw the looks. I realized that if I ask people on the way in the door what they hate most about math, or what they struggle with most in math, 4 out of 5 people will usually say fractions. So if you don't like fractions, trust me, you're not alone. Just to review a little bit, that top number is called numerator. The bottom number? Denominator. Just a little side note reminder that you saw me pause in the middle of that. I am a horrible speller. Every now and then you'll see me pause in the middle of the word, which means I got halfway through it and I forgot how to spell it. I also realize that my handwriting sometimes leaves something to be desired. So if anything ever appears up here that you can't read, I assure you I intended it to be in English, but I probably either butchered the spelling or my handwriting was just off. Don't be afraid to ask me what something says. I will not be offended. I know that my writing is sometimes horrible. So numerator and denominator, let's take a look at it. What does it mean to numerate? Well, every 10 years our government does a census. So they send out people to numerate the population. What are they doing? They're counting. Good. Well, you can probably see where this is going. Denominator, we have different denominations of money, different denominations of groups and religious organizations. To denominate means to classify or to give a name. So a fraction, or numerator and denominator, are just a count and a name. A lot of people look at these and they see two numbers, but it's not. It is a single number with two parts. Just like we might have 3 inches or 3 cows, here we have 3 of the 7ths. So the 7 is the name here. With that in mind, then the same rules apply for adding fractions as they do for adding any other number. Now, way back in 3rd grade, your 3rd grade teacher told you, when you add fractions, you must have common denominator. That's not a special rule for fractions. That applies to all numbers. When we add numbers, we must have the same name. That's having our common denominator. They also told us that when you add fractions, you're going to combine the numerators, add the numerators. 3 plus 2 is 5, and keep the common denominator. Again, nothing new. When we add any number, we combine the counts, and then we keep the same name. It just looks different with fractions because fractions look a little different. What if I have 1/3 plus 2/5? Can I add them the way they are? No. Right now they don't have the same name. When we look at fractions in a little more depth, we'll look at how do we change that name so that we can add them. Over on the multiplication side, we think back to that 3rd grade teacher. How did they tell us to multiply fractions? Just multiply straight across, right? 3 times 3 is 6. 7 times 7 is 49. Again, that's not a special rule for fractions. When we multiply any numbers, we combine the counts, and then we also combine the names. So 3 times 2 is combining the counts to get 6. 7 times 7 is combining the names to get the 49. Well, what about if we had 1/3 times 2/5? Do we need the same name to multiply? No, we don't, because we're just going to combine the counts. 1 times 2 is 2, and then also combine the names. 3 times 5 is 15. No special rules for fractions at all. Let's keep going. Let's look at another form of number, our decimal. So 0.21. The formal way of pronouncing that would be 21 hundredths. Good. Well, written out like that, it's pretty obvious what's the count and what's the name. So if I were going to add 2 decimals, let's say 0.21 plus 0.3. Is that going to work like that? No, why not? Okay, we have to line up our decimal points. Why? Okay, yeah. Not just because our 3rd grade teacher said so, but because when we look at these, this was 21 hundredths, this is 3/10. They have different names, like you said. Now, fortunately, we just put a 0 there, and now this is 30 hundredths. They have the same name now. So when we have that 0 there, the decimal points automatically line up. So lining up the decimal points is nothing more than making sure they have the same name. Now we add 21 and 30, make 51. Where's my decimal point have to go? It just comes straight down. When we add, we keep the same name. Well, 21 hundredths and 30 hundredths have to give us 51 hundredths. Moving the decimal point straight down is just keeping the same name. Again, it's the same rules as we had for whole numbers and for fractions. It just looks a little different because it's decimals. When we multiply 0.21 times 0.3, do I have to worry about lining up the decimal point? No, because when I multiply, I don't need the same name. 21 times 3 is 63. Where's my decimal point go? Okay. I have to put a 0, so I have 3 decimal places. Why? You've been told you have to count 1, 2, 3 decimal places in the problem, so you have to go backwards 1, 2, 3 decimal places in the answer, right? Well, when you brought it up right there, this is hundredths, This is tenths. When we multiply, we do combine the counts. 21 times 3 is 63. But we also combine the names. Hundredths times tenths is thousandths. So when we're counting those decimal places in the problem and putting that many decimal places in the answer, all we're doing is combining the names. Any questions? So you can see it's the same set of rules for every form of numbers. We've got time, so let's go one more notch. Let's look at 4x. Algebraic numbers. A lot of people start to get nervous when they see the letters coming in here. 4x is just a count and a name. 4 is our count, and x is our name. Just like 4 inches, 4 cows, 4 sevenths. This is just 4x. The difference is we know what a cow or an inch or a seventh is. We don't necessarily know what x is. But it doesn't really matter. It works exactly the same way. If I had 4x plus 11x, I'm going to combine the counts. 4 plus 11 is 15, and I'm going to keep the same name of x. What if I had 5x plus 2y? What do I get? Yeah, I get 5x plus 2y. Just like 5 feet and 2 pounds, I could not add or subtract them because they have different names. It just stayed 5 feet and 2 pounds. Same here. X and y are different names, so it just stays 5x plus 2y. On the other side over here, if I'm multiplying 4x times 11x, well, I combine the counts. 4 times 11 is 44. But I also combine the names. So just like inches times inches became inches squared, x times x becomes x squared. Exact same rules as for working with whole numbers. What about 5x times 2y? Can it be done? Yeah, because when I multiply, I do not need to have the same name. I combine the counts. 5 times 2 is 10. And then just like feet times pounds became foot pounds, x times y becomes xy. Again, just like working with whole numbers. So it is the same rules for whole numbers, fractions, decimals, algebraic numbers. They all work exactly the same way. So you might be looking at this thinking, okay, that's kind of interesting, but how do I apply that to the bigger stuff that we do every day? Well, the concept that ties everything together for us is the concept of place value. Another one of those very basic concepts that has way more importance than what we give it credit for. We're going to start at the end of a number and work our way backwards. So what's this last place value, or first place value, however you want to look at it? It's the ones. Next would be tens, and then hundreds. Those are actually the only 3 place values. They just repeat. Ones, tens, hundreds. Ones, tens, hundreds. Ones, tens, hundreds. And so on. Ones, tens, hundreds again. This is our base group here. This then is what's called the thousands group. This is the millions group. So when we name a place value, we name its place value and the group it's in. So this would just be the tens place. This is the 10 thousands. This is the 10 millions. Up here would be the 10 billions and so on. Now, I'm not going to insult you by going through how to pronounce a number. I'm going to assume you guys know all that at this point. But there are some important things about this that I do want to point out. If I have 3,629, we're used to seeing it written like that. But that is really not the full number. That is just an abbreviation for the number. The full number, or the full form of that number would look like this. It's 3 1,000s, or sometimes we just say 3,000s, and 600s, and 2 10s, and 9 1s. That is the full form of the number, sometimes called the expanded form of the number. When we see a number written out like that, it tells us a lot more about how it works. First of all, you can see right here that every digit of that number is a count and a name. This is not just a 6, it is 600s. This is not just a 2, it's 2 10s. So every digit is a count and a name. And when we look at our other operations with larger numbers, we're going to see how that comes into play. Now, the other thing that we have to be careful about these abbreviations is, let's say I give you the expanded number 2,000 and 8 10s and 3 1s. What's missing there? Hundreds. There's no hundreds. Oops. Go back here. Now, I don't have to write them in here because there aren't any. And this is written out like that in that full form. The place values are written there. The names are given. But when we go to abbreviated, of course, we have to account for that. We have to put that 0 in there in the hundreds because the position of the digits tell us what their name is, what their label is. The other thing that makes our place values so important is for the process of rounding. If I give you 3,854 and I ask you to round to the nearest 1,000. Well, what's that going to round to the nearest 1,000? 4,000. And you all know how to do that. What it's really asking you to do, a lot of our basic processes in math come down to a number line. When we're asking you to round to the nearest 1,000, what it's saying is we have a number line that is labeled in thousands. And what it's asking us is if I put this number on the number line, which would be somewhere in there, which of those thousands is it physically nearest to, closest to? And it's obviously closest to the 4,000. So it rounds to 4,000. Now, you obviously don't want to draw out a number line every time you have to round a number. So what's our shortcut? Well, when we're rounding to the nearest 1,000, that's telling us to find the thousands digit. What digit's in the thousands place in this number? The 3. So we find the 3. Now, what that's telling us is that it's between 3,000 and 4,000. So that's the information we're getting from that. Then we need to figure out which one of them it's closest to. To do that, we look at the next digit, which is the 8. Now, 5 being right in the middle, 1, 2, 3, and 4, of course, would have been closer to the lower one, the 3,000. 6, 7, 8, and 9, of course, would have been closer to the higher one, the 4,000. So that tells us whether we go down to the smaller one or up to the next one. 8 is obviously closer to the top, so it goes up to 4,000. What if I gave you that same number and asked you to round to the nearest 100? Well, what's our 100 digit? The 8. We look at the next digit, and that's a 5. Now, if we're thinking of our number line here, that 8, of course, is telling us that we are between 3,800 and 3,900. However, 5 is right in the middle. So which one are we going to go to? Down to the 38 or up to the 39? We go up to the 39. We've always been taught if that next digit is 5, you always round up. Now, there's a couple of reasons for that. One is, that's not just a 5. There's numbers after it. So it's not really right in the middle. The fact that that's not just 50, it's 54, means we are slightly past the middle. So the main reason why when that next digit is a 5, we always round up, is because there's generally stuff after that we are really past the halfway point. So we're not just, I mean, you've always been told that, oh, we've just accepted that 5's in the middle when we round up. That's not really true. It really usually is past 5. The only way it's ever exactly in the middle is if it were 3,850. Then it would be exactly in the middle. And then we have accepted that we're going to round that up. Now for you guys in machining and CNC, in precision machining, mechanical design, and even in some of the precision welding, there are some cases where you don't want to round all the 5's up. Let's say you have dimensions like this. Let's say that this is 2.375 inches. This is 5.875 inches. This is 1.125 inches. And you need to round that. Now I realize we haven't done decimals yet, but let's say you need to round it to 2 decimal places. All of these would round up, wouldn't they? Well, in most cases that's okay. But if you're dealing with precision machining and there's something that has to be really, really tight tolerances, if you round all of those up, now everything's bigger than what it's supposed to be a little bit. And when you're putting a bunch of those together, the whole thing becomes a lot bigger than what it's supposed to be. So in machining, and I mean, so far I haven't seen anything in your program in the last few years where you need to do this, but be aware you might end up at a job where they do have some processes where some of the 5's get rounded up and some of the 5's get rounded down. In order to avoid that buildup, it's called an error buildup or a rounding buildup. In order to avoid that buildup and getting a result that's way bigger than you want it to be, they have those processes. Now I'm not going to teach it in here. In here, when you see a 5 in that next digit, it always rounds up. But I want you to be aware of it. There are processes out there. If it's something you're really curious about, by the way, come talk to me and I'll show it to you. Anybody in here really curious about it? Not really? Okay. That is about all our time for the day. We actually have 1 minute left, so I'm going to end it there. Normally, this class, as I said, is a 3-credit class, but we meet 5 hours a week. So the structure is supposed to be 3 hours of lecture and classroom activity and then 2 hours of guided homework time. So normally I will not lecture right up to the end of the hour like this. Normally about 5 or 10 after, I will quit and I'll give you the homework so you have time to get a good start on your homework. Today there is no homework, so have a good night and we will see you tomorrow.